everyone. Today I'd like to talk about how to turn a mesh into a point cloud. So let me show you what I mean by that. So here's a triangle mesh of Homer Simpson, and then here's a bunch of points that I've sampled on that mesh. So if I were to take him away, there's the point cloud version of him. Now there's certainly not a unique point cloud I could get, but I want the points to be evenly distributed around the surface. And so the precise thing I'm looking for is that the points are uniformly sampled by area. And so to talk a little bit more about what I mean by that, let's actually just go back to the Cartesian plane for a second, and let's uniformly sample some points in the unit square. That's at the origin 0, 1, cross 0, 1. Okay, so what I'm going to do is, to accomplish this, let's say I wanted some number of points, I have to draw two coordinates to uniformly sample inside of the square. So I'll call the first one u, that's going to be along the x-axis. And this method here will draw a number between 0 and 1, including 0 and including 1. That's what this notation means. And then I'm going to do the same thing, but I'll call it for v. That's going to be the y-coordinate. And so if I look at these points, and let me make sure that I actually plot them equally. So this is where they show up. So they're going to show up in the unit square, 0, 1 on the x-axis, 0, 1 on the y-axis, and these are uniformly sampled by area. What that means is, yeah, there's some holes. They're not perfectly, evenly distributed. But what it means is I'm equally likely to draw any location as any other location in the square. And that's what I want. I don't necessarily want to space them exactly evenly, but I'm looking probabilistically for a uniform sample. Okay, so that's what I'm going to try to do on the mesh. And so why would I want to do this? Well, so I can think of a few reasons why you would want to do mesh to point cloud in this way. So one of them is maybe you have an algorithm that you want to test for point clouds. And you don't have very many point clouds, but you have a lot of meshes, and then this allows you to generate an infinite number of point clouds for each mesh. You just keep randomly redrawing. So make as many point clouds as you want. Another reason is maybe you have an algorithm that works on a point clouds, but you don't have an algorithm that works on meshes. So only have an algorithm that works on point clouds. And you're not able to, or you don't have time to figure out a way to do something similar on meshes, so you might as well just convert the mesh to a point cloud, use the point cloud algorithm. This, for example, could be, will often happen in machine learning. Like, we can deal with point clouds, but we can't deal with meshes. There are ways to deal with meshes, but just for the sake of argument. Okay, so finally, another reason is it's great pedagogically. This particular algorithm gives me a chance to show off cool geometry tricks and some cool Numpy vectorization tricks to speed things up. So that's enough motivation for me to make a video about this topic. Okay. Alright, so let's do a little bit of math first. Now before I can talk about how to uniformly sample a triangle mesh, I should figure out how to uniformly sample within just a single triangle, and then I'll build off of that to do the whole mesh. So let's say that I've chosen a triangle comprised of 3 points. Each of these points actually is in 3D. I'm going to draw them in 2D because that's how I can draw, and also because 3 points determine a plane. But keep in mind that each of these points actually has 3 coordinates, so I'm going to have to deal with that in general. Okay, now let me, I'll outline the triangle. I actually do this by drawing a couple of special vectors here. So I'm going to actually draw vectors to depict these two sides of the triangle. So this here is vector AC, that's C minus A. And this here is vector AB, which is B minus A. And then I also have this other side. I'll just draw it as a side for now. Although, in a moment, I will use that as vector 2. Okay, so first thing I want to point out here is these two vectors actually span a parallelogram if we think about vector addition. So if I were to take the vector AC and do the tip to tail method, if I were to add AC to AB, I would take the vector AC and put its tail at the tip of AB and then follow it over, and the tip is where I end up when I sum the two. And similarly, if I take the vector AB and add that to AC, well, I take the tail of AB, put it at the tip of AC, and then I end up at this corner over here. So I should come up with a special name for this. I guess I'll just call it tip. Okay? And so just to write down what I was saying, here if I have A plus AB plus AC, that is equal to the tip. Okay? That's also like saying A plus 1 times AP plus 1 times AC is equal to the tip. The other thing I want to point out, which is maybe kind of obvious, but I'll just write it down. A plus 0 times AB plus 0 times AC is equal to A. Okay. But what we're really interested in is something in between these two cases. So if I walk all the way along vector AB and then all the way along vector AC, that brings me all the way to the opposite side of this parallelogram. If I start at A and I don't walk at all, okay, I stay at A, great. But I'm going to think about how do I draw points uniformly within this entire parallelogram. Now you might be saying, well, why the parallelogram? You know, I want them inside of the triangle, right? I want these points here. I don't want these points over here. But actually, it's easier to sample within the parallelogram first, and then we'll reflect these points over. So let me just finish the parallelogram first, and then we'll talk about it. Okay. So here's what I want to think about now. If I do something a little bit in between, if I say A plus, we'll say U times AB plus V times AC, that's going to be equal to some other point. And so just like I did in the code a moment ago, where I let U be a number between 0 and 1 and V be a number between 0 and 1. So this is actually like a special parallelogram where the AB vector would be pointing from 0 to 1 and the AC vector would be pointing up here. But now I'm generalizing this to any parallelogram, and my claim is that if I sample like this, where U and V are in that unit interval, then this gives me uniformly sampled points in the parallelogram. Okay. So I think it's helpful, yeah, so that's the algebra behind it. But it's helpful to think of it like a picture. So what U is doing is it's choosing me some length along this AB axis here. So you can think about it as choosing a length along the axis. So let me point out what U is here. So, and let me even make this a little interval just to emphasize the fact that, you know, this is some number that I'm choosing here. It's between 0 and 1. It tells me how to walk along. If it's 0, I stay at the tail of this. If it's 1, I walk all the way to the tip. Now, once I've chosen a U, I take this other vector, and I'm going to walk by an amount V along that vector. So here we are. We're going to start here, and we're going to walk by an amount V here in that direction. And wherever we stop is where the point is that we're going to sample. So there it is. And so what you have to convince yourself is that this gives a uniform, you're equally likely to choose any point within the parallelogram. And you can see this by noticing that, okay, what U does here is it chooses one of these slices. So it's sort of like I'm slicing from the top to the bottom of this parallelogram here. U choose me what slice I'm going to be on. And then V tells me which point to choose on the line segment in that slice. So first you have to convince yourself that U uniformly samples among the slices. And then V uniformly samples within a slice. And so that's why this actually works mathematically. So this will give me points uniformly distributed within the parallelogram, not necessarily within the triangle. Okay? Okay, but what if I make U a little bit longer? And what if I make V a little bit longer? So maybe I'll go all the way down here. And then I walk even further along the other axis as well. So I'll make my V actually go all the way over here. So in that case, I may end up in the other triangle on the other side of the parallelogram, and that's not what I want. I want to sample a point inside of this triangle up here. So in order to do that, I can look at this formula and actually realize that, okay, so let me call this point P just so I can summarize this a little bit more easily here. So this formula here actually looks a little bit like another formula that we've seen in the past. I'll link to the video, using barycentric coordinates. So I'll just write it real quick. I'll say, yeah, there is actually another way. If the point P is actually inside the triangle ABC, then we can write it using barycentric coordinates. And the formula is P is equal to alpha times A, so that's the barycentric coordinates associated to A, plus beta times B, plus gamma times C. So each, basically you have three numbers, each is associated to one of the points in the triangle, and they all tell you how much of each point is involved. If alpha is large, then I have a lot more of A, I'm closer to A. If beta is large, I'm closer to B. But they have to satisfy a constraint, which is very important. So what we have here is actually, or really two constraints. So alpha, beta, and gamma have to all be non-negative. So they all have to be greater than or equal to 0. And then also alpha plus beta plus gamma, trying to reuse my Greek letters here, alpha plus beta plus gamma has to be equal to 1. All right? So just real quick to remind you what this looks like. Here I've approximately drawn the triangle. Here I'm changing alpha, beta, and gamma. Notice as I pull beta up here, it ends up at the tip of, or it ends up at beta there. But notice that makes the other two coordinates 0 because they all have to add to 1. If I now make beta go down, but I make alpha go up, I start to walk towards A. And then if I, let's say I have a little bit of each one of these, well then I end up kind of towards the middle of the 3 points, right? And just a sanity check, if I make gamma 1, I end up at C there, you see? So that's the way barycentric coordinates work. Now if I go back to the original equation, and I write this out, I can come up with a relationship between the barycentric coordinates and U and V. So these vectors that I was adding were actually differences of these 3 points. And so what I can see is, all right, if I write this out, what I get is this is equal to A plus, or I should say A times 1 minus U minus V plus U times B plus V times C. So this is just using the distributive rule, combining like terms, things like that. And so what this shows me here is actually U, if I'm inside the triangle, then U is actually equal to beta, the second barycentric coordinate. V is equal to gamma. And actually alpha is equal to 1 minus U minus V. So there I would say alpha is equal to 1 minus U minus V. Now if U and V are too big, then alpha becomes negative by this formula. So not only does this formula show us how to convert to barycentric coordinates from UV, but it also allows us to detect if our point has gone out of bounds, because we can't, I'm choosing U and V between 0 and 1, so they satisfy this non-negative constraint. But if I then plug them in and try to get alpha, and I get a negative number, then I'm on the outside. I'm in the other triangle. And so our algorithm is to flip, or to detect if we're on the other side. It's just check if 1 minus U minus V is negative. If it is, then we're on the other side. Okay, so we know how to detect. And so that kind of makes sense. If you look at this, like, okay, yeah, this U and V had to be pretty big to get me to the other side. 1 minus the sum of those two is going to be negative. Okay, but what do we do if we detect this? So in this case, we just have to come up with a new set of barycentric coordinates that reflects this point onto the other side. So in particular, what we'll do is let U prime be 1 minus U, and V prime be 1 minus V. And then so alpha prime would be 1 minus U minus V. or sorry, 1 minus u prime minus v prime. And so the problem before was that u and v together were too big. But, so I can actually, if I group the negative in here, I can see, yeah, the problem was 1 minus the sum of u and v was less than 0, so u and v were too big. So I'm going to make them together a little bit smaller. And that'll make it so that this third barycentric coordinate is actually valid. So if I let this be 1 minus u and this be 1 minus v, you can show that this is no longer negative. So let's look pictorially what that's saying. So 1 minus u is the amount that I have left to walk down here. Alright, so I'm going to call that u prime. And then 1 minus v is the amount that I have left to walk in v if I want to get to the other side of this segment. So I'm going to call that v prime. Okay, so what point is that giving me? Let's look and see, like, what do I actually get if I use these barycentric coordinates starting from the beginning here. So let me walk down u prime, and then I'll walk over v prime here. And I end up at a point p prime, I'll call it, that's here. And if you think about it, this makes sense. This is going to map the entire triangle. It's going to fold the whole triangle over in a consistent way, because you could also think, like, what I've really done is I've imagined what it would be like if I started walking at the tip up by u prime. All right, you can see that another way to get to p would be to start at the tip. So I'm just showing really what I just did algebraically. I'm going to show it pictorially here. So the action of making this 1 minus u and 1 minus v is to say, okay, I'm going to start at the tip here, move up in the other direction by u prime, and then move left the other direction by v prime. So I guess I don't have to color the picture here because we can see in both instances this is v prime. But yeah, so it's like walking up this much by u prime, walking to the left this much by v prime. That gets me a point in this triangle up here. But now I'm going to say, well, no, I don't want to use the tip. I want to use A. And so it reflects it over to the other side. All right? So that's how we can fix it up. So let's try to do this in code. I'll see if I can sample from a parallelogram spanned by 3 points and then reflect the points back that aren't valid. So I set up some points here that are a little bit like the points that I showed there. I'm going to keep them in the plane just so I can plot it a little bit more easily. So let me plot those real quick. All right, so you can see the triangle there. I did have to adjust the y coordinate of C a little bit to get it to look more like it was in the picture here. So not exactly, but close enough. All right, so now let me go up and grab the code that I had before that was sampling the unit square with u and v. Now I'm going to sample the parallelogram, and then I'll work to flip the ones around that need to flip around. But let me start with this first. And so what I'm going to do is use a little bit of Numpy broadcasting here. So I need to set up this vector AB. So say AB is equal to B minus A, right? And then this vector AC, which is equal to C minus A. And let me set up my samples to be, so here's where the broadcasting comes in. I'm going to put, each point is going to be across its own row in the matrix, so let me make AB be a row vector. But each point is going to be scaled a little bit differently depending on the random choice that I made in U. And so each row is going to be different. So let me scale each row by broadcasting U down these columns here. Actually, let me start just by plotting that. So if I were to scatter just those samples. Okay, I'm going to get a bunch of points that are on this line segment. But I need the other line segment, AC, to move me over. And so let me add that one in as well. That would be AC times V. Actually, I should be making my axis equal here. Okay. All right, anyway, so there it is. And now I can see that what I've done is sampled these points inside of the parallelogram spanned by these two vectors, just like I said it would. So I need to detect, before I do this, I need to detect all the places that I need to flip. So I'll say needs flip equals, I'll say u plus v greater than 1. And so I'll say u needs flip equals 1 minus u, at whatever those were, I'll flip those. And then v needs flip equals 1 minus v needs flip. I mean, I love Numpy, man. It's so cool that you could do this element-wise indexing, things like that. And there we go. We have our triangle. Okay. So this is actually the hardest part. Now we're going to do the victory lap sampling from a triangle mesh. Okay, so to do this on an entire mesh, we're going to need to do a meta step here. And first, yeah, I'll draw a simple mesh to kind of illustrate what I mean. We're first going to need to choose which triangle to sample from. So let me come up with kind of a simple mesh here, with just 3 triangles to start off with. I'll make them different sizes. So I'll call this triangle T1, and actually I'll come up with a color for that, so it'll be red. Call this one T2, this one I'll make greenish. This one will be T3, I'll make it bluish. And so if I'm sampling points randomly in here, in this little triangle mesh, more of them should show up on average in T1 than in T2 or T3, right? So the way to do this algorithmically is to first, before we run the algorithm I talked about before, make a choice about which triangle we're going to sample in. And we'll make that choice based on the areas of these triangles. So the classic way to do that is to come up with an interval, and we'll lay out sub-intervals in this interval. So I'll say this is, again, I'll make it between 0 and 1. I will lay out some sub-intervals here that are proportional to the area of these triangles. So it looks like T1 takes up almost half of the total area of this mesh. So maybe, we say, I don't know, let's say 0.45 for the sake of argument, maybe almost a half. So what I would do is make everything between 0 and 0.45 go to that first triangle. So I would choose a number that was between 0 and 0.1, and then I would say, okay, I'm going to randomly sample in triangle T1 if that number is less than or equal to 0.45. And then I also have to partition the rest of the interval here into T2 and T3. So maybe I'll say, okay, so here's T2, and maybe I'll say here T2 gets between 0.45 and maybe 0.75, let's say, for the sake of argument. Of course, this will be dependent on their areas, but 0.75. And then, of course, the rest, in this example, is only one more triangle. T3 gets the rest from 0.75 to 1. And so you can see this is proportional to the areas. If I just throw a dart on this interval from 0 to 1, it's much more likely that'll land in red than it is that it'll land in green or blue. But there is still a non-zero probability that it'll end up in green or blue. So this gets me the right probabilities over all the triangles. And then once I say, okay, look, I threw my dart at the board and it landed here. Okay, I'm going to sample from triangle 1. Now I'll run this algorithm. Now I throw a dart again. I want to sample another point. Oh, it lands here. Okay, I'm going to sample in triangle 2. Throw another dart, lands here. Sample from triangle 1. Throw a dart, lands here. Sample from triangle 3. So on and so forth. So that's what we're going to have to do in code. So going back here, what we're going to do is actually take the vertices and the triangles from the mesh and work from them. So what I'll do is I'll set up my points A, B, and C in each triangle. So I'll say A is equal to the vertices, and the first triangle index is going to be the first vertex on each triangle. The second triangle index is going to be the second vertex, so I'm pointing at B. And then the third triangle index is going to be the third vertex, which I'll call C. So this is just using some more Numpy magic to extract the first vertex, the second vertex, and the third vertex for each triangle, and to put them along a row. So the first row contains A, B, and C for first triangle, second row contains A, B, and C for the second triangle, so on and so forth. But the nice thing is I can knock out all these vectors all at once. I can say AB is equal to B minus A, and then AC is equal to C minus A. And now I can remember that if I take the cross product of AB and AC, that's going to give me a normal vector to this triangle, a vector that's perpendicular to this parallelogram, so it points in the normal direction. The magnitude of that vector is the area of the parallelogram, which is twice the area of the triangle. And so not only do I get a normal vector, which I'm going to keep that on the side, so I'll say normals equals the cross product of each row of AB with each row of AC. So I'll say axis equals 1 here, that does row by row. So that's great, I'm going to get the normals, but also I can get the areas as the square root of the sum of the squares of the components of this vector. That's going to be the areas of the parallelograms. And actually I don't want to take the square root of a negative number, so let me just clip this at 0. So let me clip that, I'll say min equals 0 here. Okay, so that's going to give us the areas of the parallelograms. And actually, let's exclude all the triangles with 0 area first. So let me actually just select a subset of these vertices here. So I'll say here, let's see, am I going to need, no, yeah, I should be good to go. I'm just going to, I don't need A, B, and C individually again. I'm just going to say A, B, and AC. So I'll say A, B, areas, let's equal 0, or I'll say AB is equal to AB areas greater than 0, and then AC is equal to AC areas greater than 0, and then finally normals equals normals areas greater than 0, and areas equals areas greater than 0. Actually, the other thing I'll do here is, okay, yeah, I need to normalize the normals. Let's do that. So I'll say normals divided equals areas. So I want to broadcast this across the columns. This is to make sure that the normals are unit norm. Because actually, as part of this, I'm going to return the normals too at each point cloud. At each point of the point cloud. So that's helpful. So I got to do that. And let me also say, I recognize that really the areas were of the parallelogram. So I want to take half area of parallelogram is area of the triangle. So that's how you get the area of a triangle, using the cross product of points in 3D. Okay, so this is great. Now what I can do is something like I did in this picture, and I got to lay these out along the interval, these areas. And so what I'll do is say, okay, I'll say interval equals the cumulative sum of the areas, and I'll divide that by the last element there. And so this is going to, I'll show you, if I say plt.scatter interval represent zeros, interval.size. Actually, there's a lot of triangles, so it's going to be a little hard to see. If I zoom in on, let's see. Yeah, so this should be going from 0 to 1. Let's see, print interval. Should be, oh, I meant to say interval divided equal to interval negative 1. Okay, there we go. So what this is going to do is exactly what I showed in the picture. So it's going to partition the interval from 0 to 1 into these little segments. Let me zoom in on a small part here. So I'll say maybe 0 to 0.05. Oh, still a lot. Yeah, there's a lot of triangles here, so it's going to be a little hard to see individual. Okay, there we go. So if I zoom in far enough, you can see, okay, here's the interval for the first triangle, here's the interval for the second triangle, here's the interval for the third triangle, so on and so forth. All right, so there's a really helpful method that can help me do the thing where I throw darts and see which interval they fall in. And it's a method in Numpy called search sorted. So what I do is I give this, the first array is the sorted array. So that's going to be these interval endpoints here. And the second array is going to be the elements that I want to find where they go in those intervals. And so what I would say is try indices equals search sorted. Okay, so I'm going to give my interval. Actually, let me come up with a more informative name for this. I really should call this interval endpoints. here. So yeah, we'll run that again. So there's all my interval endpoints. And so what I'll do is search within those, and I'll draw a bunch of random points between 0 and 1, as many as I want. And this is going to give me the indices of the triangles that I should choose. So yeah, they're kind of all over the place, but they'll be sampled according to the area that they take up. Oh, and actually one thing I should be a little bit careful about here. Let me load the mesh over again so I don't mess this up. So I'm going to load the mesh here. And actually, to be really careful, yeah, I guess actually, yeah, I guess I don't need to load the mesh again, but I will just to be safe. What I'm realizing I need to do is actually, in a second, I'm going to have to use A. Okay, so anyway, okay, I think that'll be fine. Let's draw these indices. See, they were different that time, so you know they're always going to be random samples. So now I've chosen which face I'm supposed to sample from. Now I can go ahead and generate these UV coordinates, so I can copy some of this code that I had from before, and I'll just really it's going to be incredibly similar. So once I've chosen what triangle I want to go into, actually this step is exactly the same. My U's and my V's are what they are. They're just going to be relative to whatever triangle I'm in. So here what I'm going to do is select the correct AB vector for each triangle that I'm choosing to sample. And same thing for the AC vector. And actually I want to make sure, it looks like I might have actually forgotten this before, I wanted to say A try indices. Right? It's A plus AB times U plus AC times V. And I think that's it. So let's have a look and see if we can make a similar visual to what I made before. So I loaded in these vertices, I loaded in these triangles, then I made my, maybe I'll call these new samples just to make sure I'm not accidentally using the old samples. I'll call new samples. And let's see, did it work? Okay, so green is the 100 points that I just chose, called new samples. Let me turn off the other one. Okay, so here's 100 points uniformly distributed on Homer. Let's run this again. I'll put this all in one cell and I'll run this again and see what we get. We should get something slightly different. So in fact, let me take a screenshot of this and yeah, let's do that. And then we'll run this again. Should be a little bit different this time. Let's have a look. So yeah, it's a little bit different. But we're hoping each time they're uniformly spread by area. So let's take some more points, because 100 is not really a lot for this surface. In fact, this surface has yeah, over 10,000 triangles, so 100 points is not really that much. So let's actually sample like 10,000 points. Okay, there we go. So that looks pretty convincing to me. So there you go. That's pretty much it. So if I was going to encapsulate this all in a method, of course I could do that. I would just say, and you can see the method's not that bad because I used all these Numpy tricks. So I'll say sample by area. So I'm going to need to pass along the vertices and the triangles. And from that, yeah, vertices, triangles, and however many points I want. And from that, I can get my random samples. I'll just call it samples now. So yeah, let me just test this method out by itself. So I'll say sample by area. Vertices, tries, 10,000. There we go. Okay, so I just broke it down and annotated the steps here carefully. But there's one more thing I might want to do with this. So in addition to getting these points, I might actually want to correctly report the normals at each point. Because estimating normals on point clouds is very important. So in this case, I can inherit the normal information from the surrounding vertices of each point. But that means I have to estimate the normals of the vertices of the mesh. So I know the normals of the faces, but I need an estimate of each vertex normal as well. And the simplest way to do this is to make each vertex normal be an average of the normals of the faces surrounding it, a weighted average. So let me do that. I'll say here step 1b is compute vertex normals as weighted areas or weighted averages of triangle normals of all of the attached triangles. Okay, so here I'll say vertex normals. That's going to be an array that's exactly parallel to vertices. The normals also have 3 components. I also need to keep track of the areas of the triangles that are connected to them, so I can do the weighted average properly. And okay, if I wanted to do this really efficiently using Numpy stuff, I would actually use the SciPy sparse library. If people really want to see that, I can do that. But to keep this clear, I'm actually just going to use a for loop here. Sorry. It'll be a little bit slower in this particular step, but it should be okay. So I'm just going to loop through each triangle. So each triangle has 3 vertex indices. So I'll say for ijk in tries. And for, actually, you know what? I'll use a nested loop. Ooh, okay. For try in tries. And then here I'll say for, index in try. Just to make it really clear, vertex index. And so what I'm saying is, okay, that particular vertex, I'll say vertex normals of that particular vertex. That is going to be, I'm going to accumulate there the area of this triangle. Actually, I better do try index. Yeah, so I need to know, or why don't I do a zip? So I'll say try area normal in zip tries areas normals. Tries areas normals. Okay, so what I'll do is I'll add on the area times the normal. And I need to, so that's the numerator for my weighted average, and then the denominator is going to be vertex areas plus equals area. Okay, and so then what I'll do is divide the normals by the areas at the end. So let me just make sure, first of all, I'm not going to divide by 0. So I'll say vertex areas, less than equal to 0, equals 1, just so I'm going to divide by 1 to 0. And then here I'll say, vertex normals equals, oh, actually, you know what? I realized there's something, I don't have to accumulate the vertex area. I can just normalize these normals at the end. So I'll say vertex normal length equals mp.sqrt mp.song vertex normal length squared axis equals 1. So the same kind of thing I was doing before with the triangle normals. I'm going to do that here. Clip at 0. All right, and so yeah, what I'll do is I'll divide each of these normals by, again, I'll make sure I'm not dividing by 0, so let's see, vertex normal lengths, 0, so vertex normals divided equals vertex normal length. Okay, let's just make sure this code runs before I go any further. Vertex normal length is not associated with a variable. Let's see. I meant to say here just vertex normals. There we go. All right, so anyway, the code runs, but I'm not finished yet. This gives me the normals of each vertex. But now what I need to do is interpolate them properly. And so it's going to depend on which triangle I choose, which vertices are attached to it. And it's also going to depend on, so I'll say here step 5 is compute normals of each sampled point as a barycentric weighted sum of the normals of the vertices on this triangle. So here I will say I'll extract the vertices again, or I guess I'll extract the normal. So I'll say n, or normal A, is equal to, that is going to be vertex normals at So it depends on which triangle I chose here. So I'll say tries. This is getting a little messy. But I'll say, yeah, tries, try indices 0. So that's normal A. Normal B is going to be whatever the second index was, and then C is going to be whatever the third index was. And what I need to do now is sum those up. So I'll say normals of these samples is going to be the barycentric coordinate. So actually that's just going to be 1 minus u minus v, right? That's alpha times normal A plus u times normal b plus v times normal c. And of course I need to be careful here because these are one-dimensional arrays. They need to element-wise multiply by every component of these 3 element vectors. Okay, so anyway, I think I got it. Let me return the normals. Oh, I do need to normalize them, so I'm going to need to do one more step, just like it did up here. It seems like I'm writing this code over and over again. I probably should encapsulate this code somewhere else, but I'm just going to copy it here. So yeah, it's just going to be very similar. Just making sure that I don't accidentally divide by 0 here, and I want the normals to be normalized. Okay, so let's make sure that that code runs. Tuple object has no shape. So that occurred. Yeah, okay, yeah, because I'm returning 2 things here. Okay, so let me call this separately. So let's say, we're going to say now samples normals is equal to that. And now let me draw the normals. So Polyscope has, let's see, I always have to remind myself, this has a method register, let's see, curve network I think is the one I want. So yeah, I'm gonna have to draw a whole bunch of line segments coming out of that. Let me just figure that out for a second. Okay, so the code that I came up with here just makes a bunch of edges between 2 points. The first point is the actual sample we took. The second point is the sample plus a little bit in the normal direction, so moving out along the normal. So it's going to make a whole bunch of those line segments. And when I do that, I get this. Let me change the normal color a little bit. So the normals, so they stand out. Let's make them, yeah, orange or yellowish. Yeah, so there we go. So if I look at a particular point on the point cloud, I can see that these vectors are pointing out. So yeah, that looks pretty good to me. Alright, so that's it. I hope you enjoyed the video, and you can see that actually the code is not too bad to do this, especially when you use Numpy vectorization. It keeps it really fast, and it's easier to write more complicated things without having to write a whole bunch of loops. Let me know what you think in the comments. And I will be coming up with more geometry videos soon, so stay tuned. Thanks for watching.